Okay, welcome back. This time we want to look at more probability applications, and I kind of introduced it a little bit in the last section. For example, with this one where we rolled a die that such that two of the sides were red, two of the sides were blue, and one of the sides was yellow. So how many possible ways could you roll three die in a row? So could you get a red, red, then blue, then red, blue, red? We're going to learn this time that the way to do it is just to count up the number of possible ways every roll can happen and then just multiply the ways together. So in the first case you could get red, red, red. In the second case you could get, in the first case you could get a red, blue, or yellow. In the second case, same thing. In the third case, same thing. And when you multiply them together, you get 27. And that's the number of things that go into that sample space. Okay, so it's going to help with probability. And additionally, they're going to kind of build your intuition with respect to this. So, for example, on your first roll, you either get a red, a blue, or a yellow, right? And then on your second row, you'll get either a red, a blue, or a yellow. Okay, and that can happen for all three of these, right? So you get a red, a blue, or a yellow. If you first roll a blue, if you first roll a yellow, you're going to get a red, a blue, or a yellow. And then if you roll again, each one of these, you get three, right? So you get a red, blue, or yellow. Here, it's either red, blue, or yellow. And then here, red, blue, or yellow. Here, red, blue, or yellow, etc. Right? Red, blue, yellow, red, blue, yellow. Sort of running out of room. So from this guy, you get a red, blue, or yellow. From this guy, red, blue, or yellow. And then finally this guy, red, blue, or yellow. Okay. You could figure out all the guys in the sample space by kind of just climbing down branches of this tree. Okay, so we're going to introduce this as a tree. So one item in the sample space would be red, red, red. Another one would be red, red, blue. And then another one is red, red, yellow. Okay, so there was three there. Then there'll be three here. Then there'll be three here, three here, three here, three here, three here, three here, and three here. If you add all those up, what do you get? Well, you get the 27. Just basically just multiply them together and you get your answer, right? So, you have three choices in the first case, and then for each of those three choices afterwards, there's three possibilities, I guess we should say, when you roll it. And then for each one of those, there's three possibilities. When you multiply them together, you get 3 times 3 times 3, which is 27, which is exactly what you get if you just count them up. Okay, so anyways, hopefully that will get you to build some more intuition about how how we're going to count certain things. So the chapter begins with the the probability trees, or the possibility tree that I just sort of drew out there up there. So here we go, possibility tree. And in particular, in this case, we want to flip a coin twice. And use the possibility tree to enumerate the sample space. Okay, and we already know the sample space: HH, HT, TH, and TT. Okay, but we're going to use the tree to do it. Okay, so from the first flip, there's two possibilities, either heads or tails. And then when you flip again, two further possibilities: heads or tail after that, heads or tail after this. Okay, so the sample space. Well, there's you could follow the tree sort of branches. There's one H H. Okay, so H H. Another one H T. And another one T H. And then finally, last one here, T T. So there's four things there, and again, another way you can think of it is kind of like at each step, how many different choices are there? How many different possibilities? Well, in the first step, on the first flip, there's two possibilities, and then on the second flip, there's two more possibilities. Okay, so if you multiply those together, that tells you the number of things in the sample space. Okay, so in this case, the number of things in S is just 2 times 2, which is 4. Okay, they have some neat ones based on like the World Series and stuff like that. So like number 3, the World Series, we're talking about the first team to win 4 games wins. And then we want to know how many ways can the series be played if Team A wins 4 games in a row. Okay, so firstly, the first team to win 4 games wins. Secondly, how many ways can the games be played if one of the teams, and we'll call that Team A, wins 4 games in a row. Okay, so one thing to note is as soon as Team A wins 1 game, it's got to win the next 3 games, right? Because if it won 1 game and then lost a game, like B won a game, and then it won the next 4 games in a row, it would have actually won 5 games. So there's no way for A to lose the next game if it wins 1 game in this scenario. All right, so that's kind of weird, but hopefully that makes some sense. So at the first game, there's 2 possibilities, either A wins or B wins, right? If A wins, then it's got to win the next 4 games in a row. So A. Okay. Because at this point you can't split over to B winning, because we're presuming that Team A is going to win with 4 games in a row. And if Team B won, then all Team A would have to do is win 3 games, and it would win. But that contradicts the assumption that we're presuming that Team A is winning 4 games in a row. So this string right here is not going to work. Okay. Right, so at the second step, there's 2 things that happen. Either A wins or B wins again. Okay, if A wins, then again, it has to win the next 4 games. Okay, so we'll presume then on the other hand, B wins, right? Okay, after B wins, 2 things could happen. Either A wins. If A wins, it then wins the next 4 games in a row. Or B wins. Okay. After this, B can't win any more games, right? Because if B wins another game, then it would have won the World Series, and we're presuming that A wins the World Series by winning 4 games in a row. Okay, so it has to be that A wins, and then as soon as A wins 1 game, it has to win the next 4. Okay, so all we need to do now is just count up the number of branches that we're dealing with, or the number of strings. Okay, so there's A. So there's 1 there. And then there's B, A. So there's 2 there. And then there's B, A. So that's number 3. And then there's B. A. Okay, so we can count out those. Now there'll be a problem like that in the homework. Okay, those are a little weird. The ones we will focus more on will be like this flipping coin example, and that will illustrate then the multiplication rule, which is our next topic. Okay, so section 2 then, the multiplication rule. And basically the number of ways of counting a task if none of the steps depend on previous steps is to just multiply the number of ways to do each individual step together. Okay, so I want to write it in kind of a shorthand way. I'll say if the first step can be done in m ways, and the second step can be done in n ways, where the second step does not depend on the first step, this is not the shortest way to explain this, but oh well. The number of ways to perform the task is m times n ways. Okay, and then that applies to multiple steps. Like if you have 5 different steps, you can just multiply the number of ways to do each step by each other and you get your answer. Okay, so first off, let's look at number 8. And basically we have a computer store. You're going to like Best Buy or something. I don't know where people buy computers anymore, but the 3 types of CPUs to choose from, and then you got 2 types of keyboards, and then you got 2 types of printers. Okay. First, we're going to use a possibility tree to kind of enumerate it, and then we'll use the multiplication rule to tell how many different kinds of computers there are. Okay. Please note, none of these steps are dependent on the previous step. For example, if I buy a certain CPU, it doesn't restrict the different kinds of keyboards I can buy, that sort of thing. Okay. So the first step, we're going to buy a CPU. There are 3 different kinds. And then the second step, there's 2 possibilities for keyboards. Okay, so 1 or 2, and then 1, 2. Should have made my tree a little bigger. And then on the third step, there are 2 possibilities for printers. 1, 2, 1, 2, 2, 1, 2, 1, 2, and then 1, 2. Okay, so the total number of possibilities you can get just by counting up the number of quote-unquote leaves. These things right here are the leaves of the tree. Okay. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 of them. Okay, so there's 12 different computers. And let's use the multiplication rule now. Okay, so the multiplication rule basically just says, and I kind of do it like a slot thing. So I'll say this is my first task, this is my second task, this is my third task. So in the first task, there's 3 different ways to do it. In the second task, there's 2 different ways. In the third task, there's 2 different ways. If you multiply them together, 3 times 2 is 6 times 2, you'll get the same answer. Okay, so visually in your mind, you can think of it as a tree, where you're just multiplying each of these guys together. Okay, so 2 or in this case, well, we're not multiplying these numbers together. We're multiplying. So in this, the number of branches. Okay, so 1, 2, 3 here, and then for each one of these, there's 2. So it's more like you're kind of just looking at, I don't know. So at each point, you're just looking at one individual point, right? So it's like, firstly, there's 3 branches coming off, and then take one individual point here, and there's two branches coming off. Okay, and then take one individual point here, and there's two branches coming off. Okay, so 3 times 2 times 2. Hopefully that makes some sense. Okay. Let's look at some maybe license plates problems. Okay. And we'll look at some problems in the homework too on WebAssign. Okay. There's license plates, and license plates are 4 letters followed by 3 digits, and you're allowed to repeat the letters and digits. Okay. So it's a license plate. With 4 letters, like A, B, A, Z, and then followed by 3 numbers, like 9, 1, 9, 2. Okay, and you're allowed to repeat numbers. Okay, so basically you have 1, 2, 3, 4 choices for the letters, and then 1, 2, only 3 digits. Sorry, so 919. Okay, and then 3 numbers. Right. So in the first decision, there are 26 basically branches, one going to A, B, C, D, E, F, G, all the way down. And then the next decision, each one of those dots has 26 more dots coming from that. Okay, and so on. And then when we get the numbers, there are first 10 possible choices. Okay, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then the same for the next one. Right below all of those dots, there's 10 choices. Okay. And then if we multiply them all together, you get 26 to the 4th times 10 cubed. And I think on WebAssign, you actually have to multiply those things out, okay, and write in a number. Okay, let's try number 11. How many bit strings have length 8? Okay, so bit strings used in computer communications. An example of an 8-bit string would be something like 11011000. Okay, and you can have a 0 in the beginning too. So another example, 000010000. Okay, that would be another example. Okay, so how many of them are there? So this is part A. Well, you have 1, 2, 3, 4, 5, 6, 7, 8 sort of tasks before you, and each task has 2 choices, right? 0 or 1, and then below those guys, 0 or 1, etc. Multiply those together and you get 2 to the 8th. Okay, part B. How many begin with 3 zeros? Okay, this is no big deal. It just means that 3 of the decisions have been made for you. Right? So the first 3 tasks are already done. It's sort of like somebody already completed part of the job, and all you have to do is figure out how many different ways are there to fill in the other blanks. Okay, so I'm presuming that there's not 0 ways to do it. There's only it's already been done. You can think of those as ones, but I'm saying they put a 0 in those blanks. Maybe I should put those below. Okay, so they put a 1 here, and then they chose a 1 here, and then they chose, they put a 0 here, and then a 0 here, and then a 0 here. There's only one way. It's like you have a dot here, you chose 0, okay, and then you chose 0 right there. So at each point, there's only one branch coming off. So there's only one way to really do that. And then for the rest of them, there's 2 ways. Okay, so it's just going to be 2 to the 5th. There's harder problems. We'll get there. Okay. In the meantime, let's look at the permutations now. Okay. Okay. These are the number of ways you can kind of mix up 3 objects or n objects or how many other objects you want. Order matters. Okay. So like ABC is different than CBA. That's important. And repetition at this point, we'll kind of keep that separate. Okay, so anyways, let's look at an example. Okay, before I get in too deep try to teach everything in 1 second. We want to find the number of permutations of A, B, and C. Okay, so what are they? There's ABC, there is BAC, there is BCA. Okay. What else? There's ACB. Okay. And then the ones with C coming first, C, AB, and CBA. Okay, so how many? 1, 2, 3, 4, 5, 6 of them. So the number of things in this set, the number of permutations of ABC is 6. Okay. How can we do this in terms of like a possibility tree? Well, the possibility tree version isn't, the choices are dependent on each other. Okay, if you remember back here in the multiplication rule, it said the second step does not depend on the first step. Okay. Okay, here it does, because note in our permutations we never said A, C, or anything like that. We can't repeat things. Okay, so no repetition allowed, I guess. Order is important, no repetition. So at the first task, you have 3 choices, either A, B, or C. Okay, and then the second one, if you pick A, then you only have 2 possibilities left over, either B or C. Okay, and then if you pick B, then you automatically have to go with C. If you pick C, you automatically have to go with B. Okay, and then if you pick B here on the first choice, you have 2 choices, A or C. Okay, if you pick A, then your last pick has to be C. If you pick C, your last pick has to be A. Okay, and then here, if you pick C, then you have to pick either A or B. If you pick A, then your last pick has to be B. If you pick B, your last pick has to be A. Okay, so there are 1, 2, 3, 4, 5, 6. Okay. All right, so how do we do that using kind of a multiplication principle? Well, you could still kind of play that game, right? The only problem is now, once you have picked one, you have one less to pick from. So in the first choice, in the first task, there are 3 possible letters to pick from, right? So you can see that right here. There are 1, 2, 3 things to pick from. Then once you pick that one thing, like right here, there's only 2 left. Okay, so in the next task, there's only 2 ways to figure that out. And then the third way, once you get to that second letter, there's only 1 possible choice to make, so it's 1. And look, if you multiply that together, you get 3 times 2 times 1, in other words 3 factorial, which is of course 6. Okay, and that becomes the way to do permutations. And in general, then they give this as a theorem in the book, theorem 9.2.2. And it says the number of permutations of a set with n elements is n factorial. Okay, so we'll have these kind of anagram problems where how many ways can you rewrite the word computer, for example. Okay, so it's just an example. I think it's in the book. How many ways? And then I think we'll look at sort of our permutations next. So how many ways can we rewrite the word computer? Okay, so note the word computer has how many letters? 1, 2, 3, 4, 5, 6, 7, 8. None of the letters are repeated. Okay, so permutation should work well. Right? So we have 1, 2, 3, 4, 5, 6, 7, 8. The first task, in the first sort of task, we have 8 choices, 8 letters to pick from, right? And then once we pick one of those letters away, there's only 7 letters to pick from underneath that. Right? So if you think in terms like you have a tree in your mind. And then under those 7 choices that you may have previously made, there's only 6 possible letters left. And then you just keep on going on. And so we get 8 factorial. Okay. Different kind of problem is if you just want to know how many ways can you rewrite the word, maybe like 4 letters out of that word, right? So maybe just pick M, P, U, T and then write those or something. What I'm getting at are these problems called R permutations. Okay, so this is the next section. Getting ahead of myself again. R permutations. So you'll have n things to pick from, and you're only going to pick like a subset of them. Okay, so maybe you have 8 things to pick from, you only pick 4 of them. How many ways are there to how many different words can you form if you pick 4? So in the previous example, 1, 2, 3, 4, again, you have the first decision, and there's 8 letters to pick from, and then once you pick one of those, there's only 7, and then there's 6, and then there's 5. Okay, so in this case, there's n things to pick from, and we pick 4 of them. Okay, this number 4 is the R value right here that I'm talking about in the R permutations. Okay, in particular, our notation for it will be NPR, or on a lot of calculators it's P of NR. And the homework, this is the way they will write that as well. Okay, so let's get in there and maybe look at some examples to get it kind of embedded in our brains. So an example, find the orderings of 3 letters picked from a set of 4. Find the number of different orderings of 3 letters picked from a set of 4. Okay, so let's say the set is A, B, C, and D. Okay, so again, you could do a decision tree. You know, first you're picking one of those 4. So A, B, C, or D. And then once you pick one of those, there's only 3 left. So B, C, D, or A, C, D, or A, B, D, or A, B, C. Okay. So how many have we done? 2. Okay. And then for the third letter, there's only 2 choices in each case. Right. So 1, 2, 1, 2. I won't list them out. Okay, and then you could kind of count that out, right? So in the first decision, there were 4 choices. In the second decision, there were 3 choices. And in the third decision, there's only 2 choices, right? So it's not exactly a factorial. I mean, it's equivalent to 4 factorial, but it's like 4 times 3 times 2, but we're missing the times 1 part, okay? Let's find the number of ways you can order 2 letters. Okay, so this is a number of ways you can order 3 letters. Part B, find the number of different orderings of 2 letters. Right? So it's basically the same tree, except instead of going down to that third level, we're just using that part of it. So in the first case, there's 4 choices, and then in the second case, you have 3. So again, it's kind of like a factorial, but the bottom part is chopped away. That 2 is chopped away, and that becomes kind of the way to think about the formula. Okay, so it's kind of like a factorial all over divided by another factorial. Okay, and in particular, that's going to be the kind of way it works. Okay, so it's going to be like in our case 4 factorial, but not exactly, right? So what was it? It's 4 times 3. which is the same as 4 factorial, 4 times 3 times 2 times 1, all over 2 times 1, okay, which is 4 factorial all over 2 factorial. We need to put that in a more general form, right? So in general, then, the number of orderings of R objects picked from N will be given by n factorial all over n minus the r factorial. Okay? And our notation in the book is P of n r. Okay, and that's theorem 9.2.3, I think. Okay, so it's a factorial, but then, you know, it's like this is 4 factorial, but then you're dividing out by the 2 factorial, which is just 4 minus 2. In this case, it's 4 minus 3. So it'd be 4 factorial all over 4 minus 3 factorial, which is 4 factorial all over 1 factorial, which is just the 4 times 3 times 2. Okay, so let's see if we can apply this to maybe some problems. So 39, very similar to the computer problem, right? So how many ways can 6 letters of the word algorithm be selected and written in a row? From word, not work, algorithm, and then be written in a row. Okay, so there's 1, 2, 3, 4, 5, 6, 7, 8, 9 letters. Okay, so we have 9. You could do it the old-fashioned way if you want. You could just say, all right, the first choice, there's 9 to select from, and then 8, and then 7, and then 6, and then 5, and then 4. We only want to select 6, right? 1, 2, 3, 4, 5, 6. Okay, so that's one way to do it, but you can also now use the pick notation. So it's 9 pick 6, and then we could write that in factorial notation, 9 factorial all over 9 minus 6 factorial, which is equal to 9 factorial all over 3 factorial. And if you expand that out, 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, all over 3 times 2 times 1. The 3 times 2 times 1s cancel, and lo and behold, you just get what we probably thought we would get. Okay, you make some of the problems a little harder. That was part B in the book. Part C, they want to know the number of ways you can rewrite it where the first letter is A. Okay. Okay, so basically the first task has been done for you. 1, 2, 3, 4, 5, 6. Okay, so we're putting an A here. There's only one way to do that. And then after that, how many letters are left over? We're not repeating letters. Okay. After that, there's 8 letters left. So on the next choice, you have 8 possibilities. And then after that, you'll have 7, and then 6, and then 5, and then 4. Okay, so it's really, at the end of the day, there's 8 things left over, and you're picking 5 of them. Okay, and then you'll get the same answer. Okay. That's pretty much my lecture. Let's go in now to the homework and kind of see if there's any issues there. Okay. Right. So there's some proofy ones using definitions of our n pick r. These are ones like we were just doing. These are just can you evaluate 9, pick 5. Let's try this one here. So how many ways can the letters of the word dancer be arranged in a row? Okay, so this is like 17. We have the word dancer. Okay, so there's 1, 2, 3, 4, 5, 6 letters there. So part A is just 6 factorial. Okay. How many ways can the letters of the word dancer be arranged in a row if D and A must remain together as a unit? Okay, so they're saying D and A have to be together. Okay, so there's how many different ways can that happen? There's that way. There's this way. There's this way. There's this way, and there's this way. All right. And then, so what you're going to do is add those together. So in this first case, after you pick D and A, there are 4, so this is part B. There's 4 letters left over to choose from. So there's 4 different ways here, and then 3, and then 2, and then 1. Okay. So this is 4 factorial. And same here, right? So there's this position here, and then this, and then this, and then this. So on and so forth. Okay. Okay, so at the end of the day, how many are there? There's 1, 2, 3, 4, 5. 5 times 4 factorial, which of course is 5 factorial. Okay. There's other ways to look at this. Okay. Another way to think of it is just to think of the 2 letters DA as a unit all to themselves. Okay. So one letter is DA, and then the other letters N, C, E, R. Okay. And all you're doing is arranging these 5 letters, quote unquote letters. Okay. In the first case, there's 5 things to pick from. Okay. The second case is 4, then 3, and then 2, and then 1. So again, it's just 5 factorial. Okay. Many ways can the letters of the word dancer be arranged if NCE must stay together. Okay, so you can play that same game. NCE, consider that as one letter. And then you have D, A, what are the leftovers, and R. So that should be 4 factorial. Okay, 4 times 3 is 12, times 2 is 24, and yeah, that's the answer. They have some looping problems, and usually that just comes down to, okay, so this one, determine how many times the innermost loop will be iterated when the algorithm segment is implemented and run. Okay, so in the outermost loop, you're going from A to B. So when it's A, you go to this inner loop, J, and you do that loop C to D times. And then you go to A plus 1, and then you do that loop C to the D times, and then A plus 2, you do that C to the D times, and you keep going. Okay, let's do this one as a little easier first. Okay, so for I equals 9 to 60, and then for J equals 10 to 30, you execute something, do your next J. So when I is 9, you're going to go from 10 to 30. So I is 9. You're doing 30 minus 10 plus 1 things. Okay, and then when I is 10, you have to do that again, right? So you 30 minus 10 is 20, 21 things. And then when I is 11, you have to do 21 things, all the way up to when I is 60. And in that case, you do 21 things, right? So how many are there? How many times are you doing that loop? Well, this is 60 minus 9 plus 1 times. Okay, so that would be 51 plus 1 is 52 times. And then every time you do one of those, underneath it, there are 21 things to do. So in the first step, So how do I think about this? 52, it's just going to be 52 times 21. Okay. So each time there's like 21 things underneath it. Okay. And then there's 52 things right here. Okay, so 52 times 21 is going to be your answer. So it just comes down to figuring out how many times does the inner loop go, and then multiply that by the number of times the outer loop goes. Okay, and remember your formulas. If you have multiple loops, it's just multiply over and over and over again. Right. Just looking through to see if there's anything else that's weird. I think you'll be all right. Maybe let's look at this one. Suppose a certain combination lock requires a selection of numbers 1 to 25. How many choices are there for the first number in the combination? Well, there's 25 different numbers, so 25. How many choices are there for the second number? Well, again, 25, and then 25, and then you just, if you're picking three numbers, it would just be 25 cubed. In the other case, it's just 25 pick 3. Okay, these aren't that bad. Okay, we'll leave it at that then. And I think the best way to learn is just to do tons and tons of these problems until you kind of, it takes a while. Okay, it takes a while to get a good intuition about it. It takes a lot of homework. So there will be a lot of homework in the chapter 9. We'll leave it at that. Okay, thanks for watching. See you next time.